All right, so yesterday I introduced to you guys the idea of average rates of change versus instantaneous rates of change. So we focused in on doing some calculations with average rates of change, average rates of change, and we talked briefly about instantaneous rates. Can somebody tell me what the difference is between an average rate of change and instantaneous rate of change? Sam?
Average rate is like the average of, say you're talking about speed before, is the average of the speed, but instantaneous is like at one specific point.
Okay, so when we talk about average rate of change, we're talking maybe over like an interval of time or over a range of values, whereas instantaneous rate of change is at an exact moment or an exact point. We're interested in, like if we're talking about speed, it could be the average speed over the course of a trip versus your speed at an exact moment. We talked about how officers are interested in instantaneous rates of change, right? Your speed at that moment, not so much your average speed over the course of your entire trip. Whereas I'm interested in my whole speed over the course of my trip because that determines how quickly I'm going to get to my destination, right? Okay, so we're going to go a little bit more into instantaneous rates of change. So we're looking at the rate of change at an exact moment when we talk about instantaneous rate of change. So if we think about the idea of average rates of change, we can actually kind of use the idea of a secant, a really, really small secant between 2 points. So if I'm trying to find, let's say, the instantaneous rate of change at 1.5, at this point right here, how quickly is our x value changing or our y value changing with respect to our x value? If I can, or actually maybe I'll use this point as an example. If I have a secant here, and let's say I move this point closer and closer and closer to my point over here. Okay? Eventually, the hope would be that I get so close to that point that maybe I have a point right here where the slope of the secant that connects those 2 points right in there is super close to the slope of the tangent at that particular point. So if I make my interval of my average rate of change so small that these 2 points are super close together, hopefully the slope of the secant at that, between those two that small interval, will be kind of close to the slope of the tangent. So the first thing that I'm going to show you guys is we're going to kind of create a tangent line here. It would be good if you guys have like a little ruler that you can kind of bring in for some of these questions. If you don't, see if you can find something with a straight edge that you can use. But the idea of drawing a tangent line is creating a line that kind of grazes that point at that function at that one single point. So that's kind of the thought. So I want to create a line that feels like it's balanced on my equation. So I wouldn't do something like this because that's kind of unbalanced. But if I can kind of create a line here that just crosses at that one point, sorry, this is going to be hard for me to do freehand, but if I can create a line that grazes the function at that one single point and kind of goes like this, it looks somewhat balanced. If I look at the spacing here, imagine that this is kind of like a teeter-totter, right, where that line could go anywhere, but we want it to kind of look like it's balanced on both sides. So ideally, this kind of little space inside here would look balanced with this over here, right? So this is going to be a little bit more estimated than some other methods because my tangent line, as I said to you guys yesterday, might be different than any of your tangent lines that you've drawn here. So what I would want to find is the slope of this tangent line. Okay, this is going to be essentially your only option if you just have a graph with no equation. So if I didn't have this, my tangent line is really my only option, unless I can figure out the equation from the graph. So what we'll use here is, I'm going to pretend I don't have an equation for this method, so we're going to do this as if we don't have an equation. Okay, so we'll pretend that we weren't given this. I'm just going to have to estimate approximately where some of these points are for my calculation. So perhaps maybe we could use this point right here. That's the point 211. And then another point, I don't know. These are all kind of estimated points. Maybe we can use the actual point that's on here. So maybe that's like 2.5, 5.5. Okay, again, I'm estimating these points on the graph so that I can find the slope of the line that connects those 2 points there. So here we're going to call this our x1, y1, and our x2, y2. And we will find instantaneous rate of change. So remember, we talked yesterday about how when we're doing instantaneous rate of change, we use dy over dx instead of delta y over delta x to show that we're finding an instantaneous rate of change. We should be finding, sorry, we're going to have to erase this. We're finding instantaneous rate of change at 2 seconds, and I plotted the point at 2.5 seconds. Sorry. Just checking if you guys are awake, and you're not, so come on. You're testing me, I see. All right, this is the point we want to use. I just used my example point, and I went from that for some reason. This is the point we want to use. Okay, we'll draw our tangent line there. Okay, so perhaps maybe we can use this point and this point as our 2 points. So I'm going to use the point 1.512 and 9.5. Again, I'm just estimating these points, and I'm estimating how that tangent line kind of grazes the outside of that graph. So we'll use this instead as our x1, y1, and x2, y2. Okay, so the way that we're going to do this notation is we're going to say the instantaneous rate of change, so the change in y with respect to x, when x equals 2, so we're telling where we're finding the instantaneous rate of change, is approximately going to be equal to the average rate of change. Or actually, we'll say it's approximately going to be equal to the change in y over the change of x for our 2 points here. So it'll be 9.5 minus 12 over 2 minus 1.5, and we'll find the slope. Exactly? Negative 14? Yeah? Can someone else check that quickly?
Oh, I didn't know. Oh,
Negative 5. Okay, sorry. I think it should be negative 5. You get negative 2.5 divided by 0.5. And I think this is height at time, so it doesn't actually really tell us what the height is, so I'm going to say the height will be in meters, and it tells us that the time is in 2 seconds. So this will be time in seconds, so this will be meters per second. Does it make sense that the instantaneous rate of change or the slope of the tangent gives us out a negative value?
Yes,
Why?
because it's going down.
This is a line with a negative slope, right? Okay, so if I don't have an equation, our tangent line is really the only thing that we'll be able to do. So with a ruler or something with a straight edge, you try to balance that line as best you can, just so that it grazes 1 point on your function. Now, if I have an equation, so now we're assuming that we're given this, I can create a really, really small interval surrounding 2. The closer I make that interval around 2, the better my estimate is going to be. So the idea is potentially maybe I could choose points on either side of that, and I can find the slope of the secant line that connects those 2 points. So if we look here, the hope is that this secant line that kind of surrounds that interval at 2 will be super close to the slope of the tangent line because the interval is so small around 2. This is ideal if you have an equation that's given to you. So this will be our method 2. Okay, we're going to choose an interval that surrounds 2 that's super, super close to 2. So on the left side of 2 and on the right side of 2. So perhaps we can choose the interval from 1.9 to 2.1. Right? Because that's right around the value 2. Now if I wanted my answer to be even more precise, maybe I would choose the interval from 1.999 to 2.001. Right? So now I've just narrowed that interval closer and closer and closer to 2. So the closer you get, the more accurate your estimate is going to be. So maybe we'll use this for our estimate. Okay, so this is like our x1 and x2. I need to figure out what the y1 and y2 are given my equation. So I guess t1, t2 is technically what we're calculating, but we're going to evaluate h at 1.999. Okay, so I'll get a couple people out there to calculate for us. Actually, in fact, everybody should be calculating. And we're going to evaluate h at 2.001. Alexandra?
9.41.
Did you give me all the decimals there?
9.4055951.
Perfect. We're going to keep full decimal place accuracy here until we do our final calculation. Okay, let's calculate that second one there.
Bless you.
Alexandra?
9.39,43951.
Awesome. So we'll use that for our second point here. That will be our x2, y2. Okay, so we're going to say dy over dx or dh over dt when x equals 2 is going to approximately be equal to the average rate of change over the interval from 1.999 to 2.001. So we're approximating instantaneous rate of change with an average rate of change calculation, like a secant slope. Okay? So we know this will be equal to y2 minus y1 over x2 minus x1. And let's calculate. Thank you. Okay, keep full decimal place accuracy here because the minute decimals here are really going to matter once we are dividing by a small decimal on the bottom. It's going to bring the decimal place on the top over quite a bit. So want to keep all the decimals. Alexandra, what'd you get?
-5.6.
Negative 5.6 meters per second in this scenario. All right, so this is actually a pretty good estimate of what the instantaneous rate of change is at that exact moment when time is 2 seconds. How was our estimate with our tangent line? How does this compare? It was close-ish, but again, it wasn't great because the tangent line is not like a super accurate method for finding instantaneous rate of change.
What is delta y and delta x?
So
Difference between that and y2 minus y1 over x.
So this right here is just saying that we're finding instantaneous rate of change when x equals 2 or time equals 2. And we're using average rate of change over this interval to help us find that. So when I say delta y over delta x, we're finding an average rate of change. When I say dy over dx, that's an instantaneous rate of change. So we're saying we are estimating the average rate of change when x equals 2, or sorry, the instantaneous rate of change when x equals 2, with an average rate of change over this interval.
So delta y is y1 minus y2? Is it just?
It's still y2 minus y1 over x2 minus x1. That doesn't change.
It just depends on what comes last.
Oh, I thought that was going to fall. Sorry, what was your question, Claire?
So it's just a difference of as to what the difference is asking?
Yes, we're just indicating whether we're doing average rate of change or instantaneous rate of change, but we're always doing y2 minus y1 over x2 minus x1.
So if you were to ask, what if, this is instantaneous, right?
This is instantaneous, yeah.
So if you were to ask instantaneous and we did, instead of writing delta y over delta x, we wrote y2 minus y1, would you take 1.5 off of that?
Well, you need to use at least one of these, like if I'm calculating instantaneous rate of change, I should see dy over dx. If I'm calculating average, I should see delta y over delta x.
Okay.
So you need to show those notations to indicate what type of rate of change you're finding.
So that's just saying there that dy over dx is equivalent to delta y over.
We're saying it's approximately equal to the average rate of change over this interval because we're estimating instantaneous rate of change using this average rate of change over this interval here. Okay, an average rate of change is calculated over an interval. An instantaneous rate of change is calculated at a point. In this case, we're using that interval from 1.99 to 999 to 2.001 to estimate approximately what the instantaneous rate of change is when x equals 2. Okay? All right. So second example is when we're given something like a set of data in a table of values. So in this case, we're given the temperature over a 2-week span in July, and it's measured at 1 p.m. on random days. So we're going to find the instantaneous rate of change in temperature with respect to time on day 7. So I'm going to show you kind of two methods that we can use to do this. The first method is similar to our second method from above, and that would be just to take your surrounding interval around day 7 and find the average over that time interval. Okay, this is really one of the closest intervals that we can get based on our data to surrounding kind of day 7. So here's what we're going to do. We're going to estimate the change in temperature over the change in time at day 7, so when time is equal to 7, using an estimate of the change in temperature over the change in time from day 5 to day 8. Okay, so I am estimating instantaneous rate of change when the time is 7 days with an average rate of change over day 5 to day 8. So it's actually over a span of 3 days. So that's why we use this approximation sign here, because it's going to approximately be equal to the secant that connects day 5 to day 8, right? If we were to graph this out. Okay, so I'm going to consider this to be point number 2, and this will be point number 1. So I'm going to do the change in temperature from point 2 minus the change in temperature from point 1. Over the change in days, 8 minus 5. Jonathan?
Negative 1.43 repeated.
And that would be degrees Celsius per day.
No, only the 3 is repeated, not the 4.
Okay, thank you.
Not that that makes much of a difference, but.
Yeah. Not a huge difference, but I want to be precise. Okay, so approximately at day 7, our temperature is changing, or it's actually dropping by 1.43 degrees Celsius each day. This is a fine method if your days are going up by consistent amounts. So if I go 1, 2, 3, 4, 5, 6, 7, or if I'm doing 2, 4, 6, 8, 10, 12, 14, and so on, this method is the method that I'm going to use. So this is the best if your independent variable, which is usually time or something, some kind of x value, right? If independent variable changes by a constant amount. Is that the scenario that we have here? Is our independent variable changing by a constant amount here? Jeremy? It's not. It's going 1, 2, and then 5, and then 7, and then 8, and then 13, and then 14. So it's just kind of jumping around. This data was taken on random days, right? Method 2 is going to be the best method if the independent variable is not changing by a constant amount, okay? So this is the best method. Okay, so if our data is kind of random and the person didn't diligently check the temperature each day or every 2 days or whatever, they were just kind of taking the temperature randomly, here's what we're going to do. We're going to take the interval on the left side of 7, so from 5 to 7, and then I'm going to take the secant slope from 7 to 8, and I'm going to average those two things out in hopes that the data on either sides of those intervals kind of averages out to approximately what that tangent would be. So I'm using a little bit more data. I'm using this 0.7 in the middle at 7 days to get a little bit more data to create this. So here's what we're going to do. I'm going to find delta t over delta little t from 5 to 7. And then I'm going to find delta t, delta temperature, change in temperature over the change in time from 7 to 8. And then I'm going to estimate the instantaneous rate of change at day 7 by averaging those two rates of change out. So here's our first one that we're going to use. From 5 to 7, I'm going to do the change in temperature over the change in time. Get you guys to calculate that out for us. Okay, we'll leave full decimal place accuracy if possible here.
0.3, exactly.
Exactly? Okay. And this is degrees Celsius per day. Okay, and then this guy, I'm going to use now this interval. So 31.2 minus 36.1 over 8 minus 7. Be consistent with which one is your 0.1 and which one is your 0.2, right? If I have 31.2 first here, then I'm going to have the day that matches up with 31.2 first in my calculation on the bottom. Okay, I'll get you guys to calculate that one as well. Jonathan?
4.9 exact.
Negative 4.9
Yeah.
degrees Celsius per day. Okay, so here is going to be our estimate. Our estimate for the instantaneous rate of change when we're at day 7 is going to approximately be equal to the average of these two things. How do I find the average of two values? I add them and divide by 2, right? If I have a mark of 60 on one test and 90 on the other test, and those are weighted equally, I'll just add them together and divide by 2 and find out what my average is in the course, right? That's kind of what we do. So we're going to add 0.3 with negative 4.9 and just divide by 2 here. And that will give me my approximate instantaneous rate of change at day 7. Jonathan?
2.3.
Okay, so it's approximately equal to, we will put it over here, negative 2.3 degrees Celsius per day. Okay, so notice how that is different than our answer from part 1. And the reason is because this takes into consideration that middle point of data and gives us a little bit more of an accurate reading as to what that change at 7 days might be. Again, these are still both estimates, which is why we're using the approximation symbol there. Okay, this one in this scenario is our best method because our variable for days is not changing by a constant amount. If your variable is changing by a constant amount, that middle point is going to by the time you do calculations with that middle point, it's going to kind of cancel itself out anyways, and it won't really make a difference. So in that case, I would just use the surrounding interval method. Okay? Our last method that we can use as an estimate for instantaneous rate of change is what we call kind of like an interval chart or a limit chart. And the idea here is kind of what I showed you on the first slide. The thought is that if I have a graph for 3x minus 1, if I take the slopes of the secants and I move them closer and closer and closer together, eventually the slope of the secant will approach the instantaneous rate of change at that particular point. So in this case, we're looking at x equals 2. So notice how the interval is getting smaller and smaller and smaller between the x's. That idea is actually bringing us closer and closer and closer to the slope of the tangent when x equals 2. So we're going to kind of fill in our chart here. We need to calculate a couple things. So I'm going to have you guys do these calculations really quick just at the bottom here. Maybe we'll just call this f at x instead so I can show you guys what we're calculating. So f at x equals 3x squared minus 1. I need to know f at 2.5. I need to know f at 2.1. I need to know f at 2.01. And I need to know f at 2.001. Okay, so I'm going to ask you guys to quickly sub those into your function here, 3x squared minus 1. And we're just going to have these calculations ready so that we can use them in our calculation up here. We also know, in the example given to us, we know that f at 2, actually the calculation is not really given to us. So it's 8 times 3 minus 1, so 23. Okay, so I'm going to pause the video. You guys quickly calculate those using 3x squared minus 1. Yep. Okay, so we need somebody to confirm these values for us. What did you guys get?
For 2.5, I got 17.75. For 2.1, I got 12.23. For 2.01, I got 11.1203. And for the last one, I got 11.012003.
Yes, so I'm actually getting some different answers as well. The first one.
I was just comparing them at the top, like I was doing change of y.
Okay. So sorry, Alexandra, can you read the rest of them to me here?
Oh, yeah, 12.23.
Is this exact?
Yeah.
Okay.
11.1203.
Great.
And 11.0120003.
003? Okay. All right. So,
Before the 12 on the last one, there's a 0.
oh, like this?
Yeah.
Okay. So we'll put in a 0 there. Perfect. Okay, so we have these values. The reason why I need these is because if this is my x1 and my x2, I need my y1 and y2, right? So for delta y for this column, I'm going to do f at 2.5 minus f at 2 to figure out the change in the y's. So the change in the y's here would be 17.75 minus 23. and that gives us negative 5.25. Our change in our x's here is going to be essentially like x2 minus x1. And in this case, we said 2.5 would be our x2, and 2 would be our x1. So that's 0.5. Yep.
For that 2, we got 11.
Did you? 2 squared, 4, oh yeah. Why did I get 23? Weird. Yeah, this is 11. Sorry, my mistake. I'm just going to go backwards here a little bit. Again, just making sure you guys are awake this morning. Jolie's awake. Okay, here we go. So delta y over delta x here must be 6.25 over 0.5. Or sorry, I got 6.75. What is wrong with me today, guys? 6.75 over 0.5. Pardon? Yeah. So we get 13.5.
Can you just sleep through the entire class?
I think not. When is your test? Yeah, I'll talk to you guys. Actually, no, we are having a test for this. Okay, change in x's over change in y's here. That gives us 1.23. And the change in x's will give us 2.1 minus 2, which will give us 0.1. So when we do delta y over delta x, I'm just going to divide what I did in the first column by the second column, and we'll get 12.3. Okay, same thing here. We're going to do the change in y's. So the change in f at 2.01 with the change at f at 2. And that gives us 0.1203. And then the change in x's gives us 0.01. And when we do delta y over delta x, we'll get 0.1203 over 0.01. So that gives us 12.03. Okay, and then for the last one, we're going to do f at 2.001 minus f at 2, so the change in y's. Gives us 0.012003. And the change in x's. So that will be 2.001 minus 2. And then delta y over delta x. So we get about 12.003. Okay. So one thing to note is that when you do your calculations, keep full decimal place accuracy in these first two columns. In the last column, when you calculate, we usually like to keep at least 4 decimal place accuracy. These ones, we kept full decimal place accuracy, as you can see here. And then over here, this was exactly what this was equal to, so I didn't need to keep necessarily like 4 decimal place accuracy. But keep your decimals, and then keep at least 4 decimals here if necessary. Now, here's what we're going to take a look at. As we shrunk the interval down this chart, my secant slopes were getting more and more accurate to what the slope is at when x equals 2. So I want to follow what the trend is in the 4th column here. So as we look down this column, what is the slope of the secant getting closer and closer and closer to? 12. So actually, technically, this is an estimate, so we'll say it's approximately equal to 12. If you're unsure, you can always do an extra interval from 2 to like 2.0001 and see what that gives you. But I think the general trend of what this is telling us is that probably the next secant slope is going to be like 12.0003, right? So This is just getting closer and closer and closer to the value 12. What we call this trend that we're following here, we call it the limit of the secant slopes. If we're looking at what value is being approached, that's a limit, right? So as I shrink my intervals closer and closer together, the limit or the value that my secant slopes are approaching is 12. And this is very important because this is the first step to understanding what they're talking about in Mean Girls when she says the limit does not exist. So very, very important stuff that we're learning here, guys. This is also the introduction to calculus and why calculus works. So that's also a secondary important part, but mostly the Mean Girls thing is the important part here, as we know. Yeah, so, oh, sorry. I don't know where the 2 went there. Pardon? And it's Wednesday. There we go. Who's got some pink accessories?